it's this whole thing divided by FA naught, right? And I'm sure that there are about 10 things you can do algebraically to make that more appealing to the eyes, but I haven't worked through this part of the problem, so I don't know exactly the simplest way to simplify these things. And you don't really have to. Okay, so that's our new material balance equation. So the old one, infinitely simpler, right? This one's messy. Remember, little k is a function of temperature. We've already been dealing with that. Temperature is explicitly listed. Now we also have the equilibrium constant, which is also a function of temperature, right? So we're going to have to add a column to our Excel spreadsheet so that this can also change over the course of the reaction. Does anything change with our energy balance? Why? So does anybody have any reasons to think that the energy balance might change? Okay, right, it doesn't. So I erased it, it's, still there. It's the same thing. So what do I need to do to my spreadsheet? Like we said, I have to add a column for Kc. And then for that, I have to use the Van't Hoff equation, which, if you don't remember, is the equilibrium constant at some temperature is equal to the equilibrium constant at some known temperature, which they gave us one. I think it was at 300 Kelvin. They told us Kc is equal to 2 liters per mole, not 300 Kelvin, at 1100 Kelvin. Okay, so the Kc at 1100, which again is 2, plus the exponent of minus delta H reaction over R. We have that, times 1 over temperature. This is the temperature at whatever. This is that temperature. Minus the temperature for the value that we have. 1 over 1100. So that's the Van't Hoff equation. Yeah.
Is that plus or multiply to the exponent?
Multiply. Thank you. Yeah, because the ratio is equal to that. The log of the ratio is equal to what's inside that exponent. Thanks. Okay, so this is in liters per mole. Caps lock. What the hell? All right, so we're given a couple of values. I'm going to move these down. We're given Kc at 1100 Kelvin in liters per mole. Or sorry, no wait, liters. All right, so you are equal to this times the exponent -1 times. Oh shit! You guys are just waiting for me to notice, huh? It's not that smart of a classroom. Should have been automatic. We're going to run into a roadblock. No, wait, I have the internet. I think I have the internet. Thank you. Chrome is blocking the largest freaking website in the world right now. Somehow I think that's a Florida issue. Oh wait, no, we didn't need this. Alright, so the R that we care about for this equation is not the same R, right? We've got to match the units, so we want to use joules per mole Kelvin, so 8.3143. Anyways, you are, I'll make this bigger in a second. So that's just the Van Hoff. Can everybody see that? I'll make it a little bit bigger. So it's the equilibrium constant we were given, 2 times the exponent minus 1 times the delta H of reaction. Don't forget, we've got to change that to make it exothermic here in a second. Divided by gas constant times the difference between 1 over the temperature minus 1 over 1100. So the initial one, of course, is 2, because they gave us the equilibrium constant at 1100, and we're at 1100. The delta H of reaction, they say to change it to exothermic, minus 80,000. And remember that this blows up, right? So we've got to fix that. And we will. But we'll go ahead and drag this down. All right, what else do we need to change, though? So we added a column for Kc. Why did we need to do that? Does the energy balance change?
No.
No, the rate equation changed. Unfortunately, I don't have it written down. We got to do this so I can read it. I said I could read that, didn't I? I can't. Well, whatever. Yeah, I know. I just didn't want to have to warm up again. All right, so this first part, what the hell? You guys can't see this. I keep trying to do that, don't I?
Just put in the formula. Let's just do it next class.
No. We're done with this homework problem.
This is the last part, right?
Yeah, I think so. You get CA naught times 1 minus the conversion times the initial temperature. Alright, it's just warming up. We're not going to have time for you guys to enter this long-ass formula. I mean, I don't want to keep you guys. So we're just going to look at the plots, and I'll upload this to Canvas so you guys are going to have it in its long-ass formula state anyways. All I did, though, is type in what we had on the board. So hopefully you guys are capable of doing that if the time comes to it. Okay, so what happens now? The temperature is increasing. That makes sense, right? Notice that it doesn't blow up anymore. Remember that it used to blow up when this was an irreversible reaction? That's because the rate was going way too fast, way too quickly. Now it doesn't go so fast because it's now reversible, right? So the rates aren't that severe. So I didn't have to change this dV term at all. And so the temperature plot is empty. Can somebody tell me why? Right, because I had frozen the axes, and so I'll just reset those. And now you see it increases and it levels off. What is the temperature at which it levels off? Right, so we called that, at least in the last class, like an equilibrium temperature for an adiabatic reactor. Well, there it is. And now what happens to the conversion? It increases and again levels off at the equilibrium conversion. And in fact, we could have set up and solved for the equilibrium and conversion and the equilibrium temperature without worrying about the differential equation, right? We've done those examples. You have a homework like that. For that, you just have two algebraic equations.